Now we're going to work on Lahar travel times. We've already determined the slope at a variety of points down a particular path, and with that information we can characterize the shape of the volcano and use that to determine our times. Remember, the formula we have says that the slope is equal to p, a constant we will determine, times distance down from the top, which is x, raised to the minus r power. And so with that information, we can take this equation, the one that looks like this, and in order to figure out p and r, we can convert this into a form that looks like a straight line, and then we can solve for the values. And so this, as we showed before, can be, with logarithms, turned into the natural log of s equals the natural log of p minus r natural log of x, and that's essentially the equation of a straight line, where this would be the y-intercept, and that value r would be the slope, and we're going to see it will be a negative slope. Once we know the y-intercept as the natural log of p, we can easily take that, exponentiate it to get the value of p we want. So we then will have values of p and r that describe our volcano. Typically what you will find is that your values of r will be less than or greater than about 0.5 and less than something like 1.5, and values of p will be in the, say, 50 to 5,000 or something like that. But they're going to be numbers of about that sort. So we are going to determine this values of p and r by plotting our data. Our data, remember, is slope and distance. We can take the logarithms of the slope and the logarithms of the distance, and thus we can then plot them on a graph, and you have this graph paper where we have the logarithm of the distance and the logarithm of the slope. Now, if we do this in meters, which is what you want to do, all of your data is going to plot in this part of the graph. But with that, we can then take those results and we will then extrapolate them over to the value where the natural log of x is equal to 1, and that will give us the value. So for example, we might typically have some values that look something like that. If I draw a straight line, best fitting sort of straight line to that, I may have something that looks like this, say, and if I extrapolate that up, this then would intersect at a value, say, of natural log of p equals, say, 4.2, and then we could exponentiate it, where the slope of this, the slope of that line, is equal to minus r, and so then we can determine our value of r. So that's something that you should be able to do, and then the reason we do all this is that once we know p and r, then we can say that the slope is equal to p x to the minus r. So anywhere in our previous equations that we had of the variable s, we can replace it with this equation, and that then will simplify the equations. In doing that, what people have found is if we normalize or come up with a standard distance, which we call a non-dimensional or scale distance, that has been defined to be equal to the a distance that takes into effect how steep the volcano is, and thus it sort of scales the distance in a way based on how fast or slow the Lahar would travel. So our new distance, which we call z, is simply equal to x raised to the 1 plus mr over k divided by 1 plus mr over k times the value of k times c, our Chesi variable, to the 1 over k, p to the m over k. Now this looks messy, but in fact it's not too bad because we know everything in it. We've determined p, we've determined r, we already knew m and k and c, so basically this is just a simple way to go from our parameter x to our parameter z. When we simplify it a little bit, you go through all the arithmetic, you end up with that z is equal to 2x raised to the 1 plus r over 3, 3 plus r, c to the 2/3, p to the 1/3. So that's not bad, and that's actually fairly simple. You have a value of r and p, different people will have different ones, but when you plug in a distance x from the top of the volcano, a spot you want to know something about, that will be converted to your new distance z, and with this relationship, the equations for the speed and the height of the lahar can be determined. And in particular, the formulas that people have derived say that the relationship between the position in this new distance space labeled z is equal to a over k minus 1, k minus 1 over k power, t to the 1 over k, where t is now time in seconds. That's what we really want to know. We know the position. If we know the position x from the top of the volcano, we can calculate the position in z. So we know this value, and we want to solve for t. And the only other thing here is a, which is called the area of the lahar. And the area of the lahar is sort of a slightly odd parameter. If we have the mountain like this, the lahar will have a shape that looks something like this. It will be tallest up near the front, and we call this the snout. And the area of the lahar is this area. So it's as though we're looking at it from a side view. It's what a side view of the lahar looks like. So this is simply equal to the volume divided by the width. And the width would be the width of the channel. So you can look on a map or something and estimate the width of the channel. It's probably going to be hundreds of meters, maybe in some spots 500 meters, and so that will change the value. So the volume of the lahar is usually going to be determined to be some number related to the size, the volume of the rock that came off the top of the volcano. The width is the typical width of the channel, and with that we get a, and so with that value of a, we now can plug that in here, and we have everything we need. There's a similar equation for the height, and the height of the snout, that's this height here. The height of the snout is equal to 1 over SC squared to the 1/3 Z over T. And so once you know your Z, you will know your T because you've done that in the first part. You do, in this case, need to know the local value of the slope. And so, but you can plug all those things in, and when we simplify this a little bit, we get the h of the snout is equal to 1 over SC squared to the 1/3 times 2a over t to the 2/3. And so we have these equations. Now, these one can sort of solve for, but it's easier to just work with them graphically, and so that's what we'll do. We have these plots that you've been given that have the z distance that you pick, and we want to solve for the time in seconds. So for example, if we took a lahar that had a size of 1 times 10 to the 7th cubic meters, that's the volume, and we assume it's about 100 meters wide, then its area would equal 10 to the 5th square meters. And we could look at these, and a 10 to the 5th square meters would be the red curve here, right? 1, 2, 3, 4, 5. So that would be the curve, and that says that for a particular distance, we could then calculate its position relative to the volcano. And so we would go through and simply make a table that might be something on that would look like we would have our value of x that we care about. We would calculate the value of z, and then from the graph we would read off the value of t. So for example, if I picked some numbers that I had, I had a value of r equals 0.81 and a value of p that was equal to 106.6. When I plugged these in for 10,000 meters down the mountain, that became a z value of 2869, which was 360 seconds or 6 minutes. Similarly, when I was at 40,000 meters or 40 kilometers down the mountain, that was a value of 16,688. And when I read that across for my particular case, that was 4,000 seconds. So your job is to, of course, calculate these numbers and decide where you think would be a good place to put the sensors that would then be able to alert the town. So you're going to want to determine travel times to different locations, and then using that, say something about the size of the position of the sensors and how much travel time would be left.